Okay, hello everybody. Since my Tuesday class has the lab time has a conflict with the exam time, so I'm going to make a video for lab 5, okay? So for the Wednesday and Thursday class, I will still give the lecture, but for the Tuesday class students, you might just have to learn from this video, okay? But you will still have 1 week for the Q&A, and I can help you during the lab. Okay, let's take a look at lab 5. So the topic of lab 5 is two-way ANOVA. Okay, so for lab 2, we have done one-way ANOVA. So let's remember what's one-way ANOVA. So we're saying when you're comparing multiple groups and when the number of groups is larger than 2, so instead of doing lots of t-tests, we would do a procedure called ANOVA, which is an acronym for analysis of variance. Okay. And in that case, we only consider one factor. So you have only one factor that separates your data into multiple groups. But in practice, very often you see there are multiple factors. So in this case, we'll consider one more step. So consider two-way ANOVA. So two factors. So two-way, basically two factors. So imagine in a setting you're looking at, for example, for example, when you're looking at the effectiveness of a drug, right? So you might have a drug 1, drug 2, and placebo. And then you might have, for example, gender. So you have male, female, right? So in that case, sex, male and female. So in that case, we have two factors, the sex and the drug status. So in that case, we have a typical setting for two-way ANOVA. Let's take a look at the problem we have, the data set we have. So this one's called film coatings applied to semiconductor wafers. Okay, so what is it about? It's a procedure called chemical vapor deposition. Okay, I have no idea what it is. I tried to Google it, and there's a video here explaining what it is. I'm always Oh my God, Jeanette also. Um, I always think it's a good idea to understand what the the background story is for the. Okay, let's watch this and see what it is. Okay, basic tool for manufacturing potato chips bank. Okay. So something are vaporized, right? So temperature must be something important, I guess. Okay, I guess I kind of understood what it is, roughly. Okay. Hopefully you understand more than me. I did. Okay. So so the specific problem we're dealing with is we're using this to make film coating. Is that what it is? So here, experiment is conducted to various levels for operating conditions for both factors, which both factors. So we have temperature and pressure on the film thickness. So the experiment is conducted by randomly selecting one of the temperature-pressure combinations. So for temperature, we have 3 levels, low, medium, and high. Similar for pressure. So we have 3 times 3, 9 combinations. So for each combination, the experiment repeated 3 times, okay? So we have 3 times 9, 27 observations. If you take a look at the data, so indeed we have 27 observations. Again, I changed my data a little bit so the number will be different than yours. So the goal is to test the joint effect of temperature and pressure on mean film thickness. Okay, so in this case, I don't know whether thickness the higher is better, the thicker the better, or the thinner the better. But the film must be as thin as possible. Okay, as thin, so thinner is better. So as you can see, we're looking for sort of like the optimal combination of pressure and temperature that produce the thinnest film coating. Okay, and this is a very typical, a very frequently seen problem in industry, right? You want to, or like economy, you want to find some optimal combination for the conditions to produce the best results. Okay, so it's a very classical two-way ANOVA setting. So 2 factors, each factor with 3 levels, okay? And then we have one response, which is continuous response measured in angstroms, okay? Okay, so let's take a look at the problem. So questions, okay, the first question, 1A, we are looking at the design information. So the experiment unit, I guess it's a film coating. Is that proper? I guess it is, right? Film coating. We are looking at the conditions that produced the film coating, like the temperature and the pressure, and we're measuring the outcome, which is the thickness of the film coating. What is film coating? Anyway, the response variable is the thickness, and it's measured in the sky. Okay, we have 2 factors, and we have the levels. It's there. What kind of design we have? So in this case, obviously, as you can see, we have exhausted all the combination of this, right? And it's the randomly determined. So we randomly select one of the combo, okay? So in this case, we actually are controlling the factors, which we can because this is an industrial setting. Unlike previously, we were dealing with lots of life science related example. In that case, it's impossible to randomly assign, for example, sex or disease group, that kind of thing. But in this case, we can. So it's an experimental design finally, right? So for experimental design, we say we can make a causal inference, right? What assumptions should be made about the wafers? What assumptions should be made about the wafers used in the experiment? I don't know. I guess they have to be the same because the only 2 factors we're controlling are temperature and pressure. So the wafer should be the same. It's like sometimes when you're doing experiment on guinea pigs or mice, right, you want the mice to be genetically exactly the same, and you change, for example, the nutrition of the mice, and you see which kind of nutrition which results in what kind of consequence. So they should be identical, the wafers. But again, what's the relationship between the wafer and film coating? Again, you guys figure it out, okay? Okay. Oh, you have to do something. Okay, let's take a look at question 2. So for question 2, we're doing some visualization of the data. So first, we're going to do some line chart. So again, when you look at 2 factors, it's very easy to do a line chart. Like you can't see my hands now, but I'm plotting, low, medium, and high, and see what the trend. Is it increasing? Is it decreasing? Is it increasing then decreasing? That kind of trend. So we're going to do a line chart for what? A line chart to obtain the plot of mean thickness, because for each combination we have 3 observations. So here we're taking the mean. The mean thickness versus pressure, so x-axis will be pressure. By temperature means we're going to have different color or different shape for the different temperature. Okay, so let's make the figure first. Okay, so line chart. So we're going to graph, chart builder, and then we're doing line chart, and then we're doing colored ones because we have 2 factors, right? So we're doing the response, the thickness, and then thickness versus pressure, okay, and then the color by mean pressure, mean temperature, okay, and then the statistics here, the default is already the mean. I think we're good enough. Okay, so let's do okay. So what do we have? We have a line chart, and it's coming. Okay. As you can see, this is not a very good figure because by default, I think the chart builder starts at 0, which leaves this huge blank area here. I think there's somewhere you can adjust this, but if you use Lexi Dialog, you will get something prettier. Let's do Lexi Dialog. Lexi Dialog line chart multiple, because we have multiple lines, and then the line represents the mean, okay, the mean. The variable, it's the thickness. Category, it's the x-axis, which is the pressure. The defined line is the temperature, okay, and then do okay. Okay, much better. Okay, it's the same thing, but it looks better. Okay, let's comment on this line. It asks you, again, my lines might look different than yours, so don't be surprised by that. What can you conclude about the effect of temperature and pressure? So let's take a look at these two factors one by one. So first, let's look at the factor of pressure. So let's forget about the color. Okay, so for pressure, when we are moving from low to medium to high, we kind of see an increasing pattern, especially for this guy. So in general, it's kind of increasing, right? And then let's take a look at the temperature. For temperature, if you look at this is the low temperature. The low temperature has the highest thickness, the largest thickness. So which kind of means that the temperature has a negative effect on the, is it negative? Yes. The lower, the thicker it is, yes. But we do see some twist here, so it's not like uniformly, the effect is not linear, okay? What combinations of produce the thinnest and the thickest? So in my case, the thinnest appears to be here, which is medium pressure and, oh my god, what color is this? I can't really tell. I'm a bit colorblind. I think it's this one. Is it 2? Ugh. Let's say it's 2. Okay. The highest is here. The highest, so we have 3. So 3, so large, high pressure, and then blue. So here is low temperature. Okay. And then this is a visualization. Okay. And then we're going to quantify this, what we saw. So we're going to quantify using the compare mean feature. So let's do compare means. So we do analyze means. Where is it? Means, compare means. Okay, sorry, means. And then the dependent list, it's the thickness. Okay, and then for independent list, because we have 2 factors, so we're going to put 1 here, and then we're going to put next. We want to have 2 layers. Okay, the next layer is pressure, and let's do okay. So what do you get? You get kind of like a basically, for example, the first subsection, the first block, it's low temperature. So we have the first row to be the combination of low temperature, low pressure, and we have a mean of 40. Low temperature, high pressure, medium pressure, low temperature, high pressure. Oh my god. And then this one total. This total basically means a combination, the sum of all the pressure. So it's all the low temperature one, regardless of the pressure, and it's 43. Similarly, we have 2, 1, 2, 2, 2, 3, and 2 total. And then the total one is basically all the low pressure one, regardless of the temperature, all the medium pressure one, regardless of the temperature. And then this total is combine everybody. Okay. So from this, let's take a look for first the effect of temperature. For effect of temperature, we're going to compare what? We're going to compare low temperature to medium temperature to high temperature. Think about why we look at the total, because when we are looking at the effect of temperature, we don't care about pressure, so we're going to look at the total. So from 43 to 37 to 37, so I have a decreasing, right? So which means that the temperature has a negative impact on the thickness. If I look at the pressure, so again, look at total 1, 2, total 2, total 3. So increasing and decreasing. But the increasing here is pretty small, and this one is pretty big. So it's kind of have like, it's go down a little bit, but then it go up. So it's kind of a positive effect, I would say, positive effect overall for the pressure. Okay. So which case, in this case, the lowest should be, I'm going back to this, 2 to 38. 38 is my lowest one, is it? No, 37. So it's looking at this guy, so medium pressure to 34. So this is a high temperature. So this one, it should be high temperature that's produced. So it's 3, okay. But again, your figure might be different. I think the noise I added today is a bit big. Okay, so that's 2. So from this, what we have learned, we definitely see that these 2 factors have some impact on the outcome. So we should be seeing some significance from two-way ANOVA, okay? So we're going to do a two-way ANOVA. So two-way ANOVA in SPSS is underlying this feature called general linear model, okay? So we're going to use the univariate procedure. It's univariate here because the response is univariate. Excuse me. So we're going to test 2 things. We're going to examine the main effect and interaction effect. So we have 2 factors. So in that case, we have 2 main effect. And then the interaction of these 2 in main effect, we have an interaction effect. So in total, we have 3 effects. Okay, 2 main effect and 1 interaction effect. We have to state a null hypothesis for main effects and for interaction to be tested. Report the observed significance level. Okay. So basically, we have 3 hypotheses, right? State null hypothesis for main and for interaction to be tested. I think so, yeah. So basically for the main effect, so you're just saying that the temperature has no effect on the thickness, and then you say temperature has an effect on the thickness. And then for the interaction, you just say there's an interaction effect between temperature and pressure for the null hypothesis, and the alternative is it's the opposite. Okay. So let's do the one-way ANOVA. So we do analyze general linear model univariate. The dependent list is the thickness. So here, both of them are fixed factors because fixed factors means the level of your factor, the levels of your factor are fixed. Okay, so in this case, for temperature, we only have 3 levels, low, medium, and high, and there's no other possible levels. So we put both of them as fixed, okay. Okay, and then let's do okay. So we get a huge ANOVA table. As you can see, this ANOVA table is previously the one-way ANOVA table only have 3 rows. This way has more. Okay, let's take a look at these 3 guys first. So the row of temperature is basically testing the main effect of temperature. So right now I have a small p-value, smaller than 5%. So it means temperature, the main effect of temperature is significant indeed. Similarly, for the pressure, I have significant effect. For the interaction, so this is the multiplication of these 2 terms are the interaction term. The interaction term also came out to be significant. So I have both main effect and the interaction term to be significant at 5% level. And you can also see why the interaction is significant, because we see interaction in the line chart. Usually if you see interaction here, there will be significance. If you see 3 lines are parallel to each other and there's no overlap, no interaction, then usually they won't be. Okay, so that's kind of like the rule of thumb. What about the other rows? So basically the corrected model, it's the summation of these 3 terms. Corrected model equals to the summation of 2 main effect and this 2. That's why if you look at this 307, the 307 is a summation of 178, 88, and 40. Similar for the degree of freedom. 8 degree of freedom coming from 2. This is 3 minus 1 because we have 3 levels for temperature. 3 minus 1. This is 2 times 2. Okay. And then the intercept plus the corrected model plus the error equals to the corrected total. So the error here is 18, so as you can see 8 from 18 we have 26. And then the corrected total plus the intercept equals to the total. So the total is 27 coming from 26 plus 1. Okay, so it's still a very organized table, but the relationship is slightly more complicated than the one we see in one-way ANOVA. And similarly, the mean square is always the sum of square divided by the degree of freedom. And the F statistics is basically the mean square divided by the MSE, the mean square error. That's why this 38 is the 14 coming from the 38 divided by the 2. Okay, and then the p-value is coming from the F statistics. Okay, so 3a, you should be able to understand it already. I think I've talked about that. For 3b, if the hypothesis for main effects for at least one of the factors is rejected, multiple comparisons might be considered for the levels. Use the Tukey procedure. Okay, so right now we're saying that the two main effects are significant. So we're saying that, temperature has a significant impact on the thickness. But again, we don't know which levels are significant, right? We don't know whether, low and medium are significant or low and high are significant. So we do a post hoc test. Basically, we look at all the combination of the pairs, 1 versus 2, 1 versus 3, 2 versus 3, right? And then we're going to use only the Tukey's procedure. Okay. Okay, let's run this again. Analyze general linear model univariate. And then for the post hoc, we're going to choose both of them because both of them are significant. Then we're going to choose Tukey's procedure, and then we're going to continue. Okay. I think 4 is asking for equivariance. Did they ask for Levene's test? Oh, they did. Let's do the Levene's test the same now, so we don't have to run this again. Where is Levene's test? Model? No. Contrast? No. Save. Leverage value? No. Plots? No. Options? Yes. Homogeneity test, okay. Homogeneity test, and then let's do okay. So we have this, let's focus on the post hoc test. So for the post hoc test, for example, this is the temperature. So we're looking at the post hoc test on the factor temperature. When you're comparing temperature 1 to 2, you see that, again, look at the p-value. The p-value is small in both cases, which means the low temperature it's significantly different than both medium and high temperature. And we see that the difference is positive, which means that the low temperature produces significantly higher, larger thickness than both medium and high temperature. Okay. Now we have a large p-value, which means medium and high temperature are roughly similar. So in this case, if you want to produce a thin film coating, it seems medium temperature and high temperature are pretty similar because the p-value is large. And then you can look at the similar thing for the variable pressure. So with the variable pressure, we have large p-value between low pressure and medium pressure, which means these two are not statistically significantly different. Sorry. I think that's a redundant thing. Statistically different, yeah. Significantly different, better. But we see a small p-value, so which means 1 and 3 are significantly different. Okay. Yeah. So just report your conclusions here. Okay. Okay, one more question. Question 4. We're looking at the hypotheses. Okay. So the hypotheses we assume, the assumptions. Oh my God. The assumptions. Okay. So the assumptions are quite similar with the ones we talked about, linearity, independence, normality, equivariance. In this case, we are mostly looking for equivariance and normality. For 4a, we're looking for the equivariance assumption. How do we check this? We said you can use Levene's test, right? And you can also use the box plot. Okay, box plot is just like a quick way to look at that. So for Levene's test, let's see. So Levene's test, we have the table here. Use any of these, I would say usually based on the mean, but usually they give you very similar results. For example, based on the mean, we have large p-value, which means that we're not rejecting the hypothesis that they have same variance, which means it's satisfied. So there's no concern for violation for equivariance based on the results of Levene's test. It also asks for a box plot. Okay, so if we do a cluster box plot, let's do Lexi dialog again. Lexi dialog and then box plot, and then let's do cluster because we have both factors. And then the variable is the thickness. Category is, let's put temperature. Maybe put, because we previously were putting pressure as category. Temperature and okay. So based on this, again, it's so pointless in the case because think about it. For every combination, how many points you have? You have 3 points. When you have 3 points and you have a box plot, it's just very pointless, I would say. It's when you have such a small sample, it's very pointless to talk about these kind of assumptions. So that's why, based on this, you could say that some of them, like this one is my smallest one, this one is largest one maybe. This one is probably more than double this one, but again, when you have 3 points, it's just, I would say in this case, the Levene's test probably would be somehow more trustworthy because, when you have 3 points, think about it. How do you draw a box plot with 3 points? Similarly with this normality assumption, right? When you have 3 points, it's very, very much pointless to talk about normality. But based on this, right, you could say, oh, this one is extremely skewed, but come on, it's 3 points. So yeah, right, whatever you think it's reasonable here, okay. That's everything. Okay, good. So this one's pretty straightforward, right? So we are basically, the main part is question 3. Okay, so question 3, try understand. I think the most important thing is to understand the structure of this complicated ANOVA table, understand what each row represent and how's the relationship. For example, the corrected model equals to what, right? The total, how do you calculate the total? For example, if you cross some one of these out, and how do you complete this ANOVA table? So if you understand all the relationship here, so I think that's pretty good enough. Okay. And that is everything. Okay, so yes, thank you. Bye.